All right, welcome everyone to another week of GOCC. This week we have the pleasure of having Ashley Tharp speaking to us. But before she gets started, I would like to remind everyone of our community statements. And first one is that we're all learning. And the second part of our community statement is that everyone has something to contribute. So if you have things to say, you can put them in the chat, or questions to ask, you can put them in the chat and one of us organizers will ask them. Or you can unmute yourself and ask Ashley directly. And the third one is no one has all the answers. So again, we can all ask questions. And so with that, let's welcome Ashley Tharp, who's talking to us about non-crossing arc diagrams beyond type A. So take it away, Ashley.
All right, thank you to the organizers for putting this together and for inviting me. And also thank you all for coming, despite the fact that I have missed every session this semester due to prior conflicts. So as Matthias said, I'm going to be talking about non-crossing arc diagrams beyond type A. This is joint work with Emily Barnard and my advisor, Nathan Reading. Emily Barnard's at DePaul and Nathan and I are at North Carolina State University. So let's do it. Brief outline is we're going to talk about some background, get in, and then talk about non-crossing arc diagrams in type A, which is prior work from Nathan's 2015 paper. And then we're going to think about generalizing those ideas and finding analogs in type B and in type D, which are the other two infinite families of finite Coxeter groups. And then as a bonus, if we've got time, we'll talk about shard intersection orders, because I've been doing some work supervised and advised by Nathan, thinking about shard intersection orders and usefulness of non-crossing arc diagrams there. Okay, so a little bit of background to start off. A finite Coxeter group, the group being W, S denoting our generating set, is this group given using the presentation S1 through Sn, our generators, and then these relations on the right-hand side. This Si squared being the identity. If you're a geometrically minded person, you might think, oh, hey, that looks like a reflection, and it is, and you can think about it that way. And then for each pair of generators, we have this Mij getting us to the identity. And because we're in a finite Coxeter group, our assumption is that Mij is always less than infinity. You can take away that assumption and you get infinite Coxeter groups. And if you are looking to do a little bit of algebra, Mij is 2 if and only if Si and Sj commute. And that might come into play a little bit later. Also, a brief definition of a lattice in case it's been a minute. So a lattice is a poset where we have meets and joins for any pair of elements. We've got 3 examples of lattices and then one example of not a lattice, a poset that's not a lattice, because these 2 atoms on the bottom are covered by both of the co-atoms. And so we've lost the uniqueness of what it means to be a meet or a join. But that's a lattice, something that might be new, so technically maybe not background, but a lattice congruence theta is an equivalence relation on a lattice L that preserves meets and joins. So if we have x1 congruent to y1 and x2 congruent to y2, then x1 meet x2 will be congruent to y1 meet y2, likewise for joins. And so you can actually, this is an analog of a group theoretic or even a number theoretic idea of congruence. And then the lattice quotient is the result of modding out by that lattice congruence. And so you can actually think of these as squishing, contracting edges between 2 equivalent elements. And so just a fact, in order to preserve meets and joins, congruences, and so also quotients have to contract edges in certain well-defined ways that we don't have time for today. But they're also local. So they can really be defined by which edges are contracted. And if you choose certain special edges, you can say, oh, these 2 edges give us the whole congruence we're looking for. So a little example, maybe not so small, but we've got this underlying, so on the figure on the left, we have an underlying lattice. And then we've also got some pink highlighted edges in that lattice. These are the edges that identify 2 congruent elements. And so we've got all these edges, and then the figure on the right is the lattice quotient. So we've squashed the edges that are highlighted in pink on the left side and gotten a lattice on the right-hand side. This may or may not be a sublattice. Interesting thing to think about, but so lattice congruence and quotient here. And then join-irreducible elements in a lattice have a combinatorial definition, but they also have a nice eyeball idea. So J is join-irreducible in the lattice L if and only if it covers exactly one element. And the standard notation for that element that it covers is this J down star. And in our 3 examples of lattices from before, we've got the blue highlighted dots are elements from which you can only go down one way. These are the join-irreducible elements in these lattices. So again, eyeballing stuff is really nice. It's worth mentioning that on the topic of lattice congruences and quotients, lattice congruences know a lot of combinatorics, as it turns out. I'm going to leave it a little bit vague, but they're a very useful thing to think about. Okay, we're finally into type A. So permutation on N is hopefully pretty familiar. It's an automorphism on 1 through N. And here's an example of a permutation in S7. The symmetric group Sn is the set of permutations on N with multiplication given by composition. And Sn plus 1 is a Coxeter group of type An. And we'll actually see the presentation for a Coxeter group of type An. It's given by N generators. We've got Si squared per usual. And then for any consecutive set pair of generators, that I plus 1 is going to be 3. Otherwise, it's 2. And so thinking about Si being the transposition I plus 1, this makes sense. Disjoint cycles commute, fine. If we've got overlapping cycles or overlapping transpositions, they'll have order 3. Okay, let's get into the good stuff. Type A non-crossing arc diagram. So this is work from a paper by Nathan in 2015. Here's the setup. We've got N distinct points on a vertical line. We identify those points with 1 through N in order, with 1 at the bottom and N at the top. So in our example down at the bottom, we've got 1 through 6. And then we've got these diagrams, which consist of some or no curves. That's also fine. Those curves are called arcs. And arcs connect points, satisfying the requirement that an arc connects a point P to a point above that, Q. And it's going to move monotone upwards from P to Q. It can pass either to the left or right of every point in between. So here we've gone from 2 to 5, going right of both 3 and 4. We've gone from 3 to 6, going right of 4, left of 5. Those are both valid arcs. The only thing that we can't do is say, okay, I'm going to start at 2, go down to 3 and back up, or whatever is going to happen, right? That monotone upwards just says we can't go down. I'm going to erase this. Okay, so that's the idea for arcs, but then arcs in diagrams also have to satisfy these pairwise compatibility conditions. The first condition is that no 2 arcs intersect except possibly at their endpoint. So in our second figure, we've got this intersection happening here. We don't like that. Non-crossing really means non-crossing. We can't intersect. And so that's not a valid non-crossing arc diagram. And then our second condition is that no 2 arcs can share the same endpoint, or that's a top endpoint or the same bottom endpoint. So in our third figure, we've got 2 arcs that share an endpoint, but it's the bottom of one and the top of another. So this is fine. However, in our last figure, in the fourth one, we've got 2 arcs where 3 is the bottom of both of these arcs. This is not okay. We do not like this. But then also our first figure, 2 arcs that don't intersect in any way. This is a valid non-crossing arc diagram. And then because an arc really says what's the bottom, what's the top, and what do we go left and right of, we considered arcs and their diagrams up to combinatorial equivalence. So we're really understanding left, right, top, and bottom. Okay, so here are the non-crossing arc diagrams on 3 points. This is all of them. There are 6 of them. There are, by the way, 2 non-crossing arc diagrams on 2 points. We connect the 2 dots or we don't. Here are all of the non-crossing arc diagrams on 4 points. There are 24 of these. And as combinatorialists, you're thinking 2, 6, 24, factorial, permutations. And you're right. But wow, look at these, so good. Okay, so we've got this map, delta from permutations to non-crossing arc diagrams. This map is just 3 steps. So we're gonna plot, so given pi from pi 1 to pi n, we're gonna plot the points I, pi I on the plane in the first quadrant. And then when pi I is greater than pi I plus 1, we're going to draw a line segment from the I point to the I plus 1 point. And then we will, once we've done that, we'll move all of our points into a vertical line, letting the line segments bend to stay right or left of the points that they were right or left of, and also letting them kind of respect each other so that they don't look like they're overlapping when they're not. So if we have this example of pi being 6, 4, 3, 7, 1, 2, 5, we'll plot 1, 6, 2, 4, 3, 3, 4, 7. 5, 1, 6, 2, and 7, 5. So we've done all those points. And then once we've plotted them, 6 is greater than 4, we'll draw a line segment between them. 4 is greater than 3, line segment. 3 is less than 7, no line segment. 7 is greater than 1. And then 1 is less than 2, 2 is less than 5. So we've drawn all our lines, and then we imagine kind of just squishing everything into one vertical line. And this is the non-crossing arc diagram we will get from that process. Are y'all with me on this little map? Okay. Yeah, Mark.
I think so. So the lines are descents.
Yeah.
Okay.
Yes. These lines are descents, which will come in handy very soon. And this, the other thing to notice is that, well, not notice, but it's true that this delta is actually a bijection from permutations to non-crossing arc diagrams. Undoing this is really just pulling it apart in a predictable way. But yes, yeah. Any other questions about this? Okay, let's keep it moving.
Yeah, I have a question.
Mhm.
So how do you know, back to your slide there?
Let's see. I thought I did it. It's paused. Okay. Let me stop my share for a second. And then start again. Ooh, this is interesting. Share. Okay. Yes.
Yeah, so how do you know like how far to really like extend your lines from your diagram to the vertical line of points?
So
Like,
it
how do
really,
you know?
go ahead.
Yeah, how do you know that? How do you know like how far to extend your line between?
So how
vertical
far to
lines?
let it bend to the right or to the left?
Yeah.
Yeah, so it really is just a matter of, because we're doing the like combinatorial equivalence, we're just really counting like, or all that we need to let it happen is that there's space between any two lines that are like at the same height, so to speak. So if we zoom in and think about kind of this little neighborhood, it doesn't matter really how much they bend because they're just both to the left. What we couldn't do though is like what we don't want to happen, and so what we kind of just think about is we don't want our inside line to actually smush to the outside. This is one way of drawing them. I've also seen them done with like using really just semicircles centered at the correct places.
So my question is that when you're taking your planar diagram to, oh, okay, it's different. I was thinking, well, why not just create, non-intersecting arcs, but you need to preserve the points in their y coordinate structure, right?
Right.
In order for this to work.
Yes.
Right. It's different than just some Catalan number counting argument of. Right.
Correct.
Cross. Yeah. Okay. Good. Okay.
Yeah.
I see now. Good.
Great. Thank you for the question. Okay. And then we've got this map, and we've also got the weak order on S4, which is a weak order on A3, and this is the right weak order. So the way that we go up in this post set, this lattice, is we can swap any two adjacent elements. So to go up from the identity, we can swap the first two entries, the middle two entries, or the last two entries. And this is how we build the weak order. It's a pleasant way to spend an afternoon if you've not done it. But so here's our weak order. And then brief facts about the weak order. First, it's a lattice. Also, it happens to be the Hasse diagram. Its Hasse diagram is the one skeleton of the permutahedron, which is a simple polytope. And then going up by a cover in the weak order is swapping to adjacent entries to create a descent. So going down would be swapping two entries to destroy a descent. And then the join-irreducible elements, the elements from which you can only go down one way, are the elements with exactly one descent. I have bolded those elements here. And it's, again, just an eyeball thing of what do we only have one way going down. But here they are. Join-irreducible elements in A3 end up being the permutations which correspond to non-crossing arc diagrams with a single arc, which makes perfect sense because, as Mark pointed out so astutely, we draw an arc exactly when we have a descent. So we've got these single arcs that represent join-irreducible elements. Or not, we've got diagrams given by these single arcs. And so lattice congruences know a lot of combinatorics. Non-crossing arc diagrams also, it turns out, in a sense, know a lot of combinatorics. And so we would want to think, okay, is there a way to use these non-crossing arc diagrams, which are a visual tool, to think about lattice congruences, which are otherwise kind of hairy to get in the weeds with. And so there's this idea of forcing. So we're going to remember congruences are defined by which edges are contracted. In the weak order, edges correspond to descents. And also, because of this delta, this map, descents correspond to arcs. So we've got this definition of forcing. An arc alpha 1, which corresponds to a join-irreducible J1, forces alpha 2, corresponding to J2. If whenever a congruence contracts the edge down from J1, it also contracts the edge down from J2. And so we can use this forcing idea to think about congruences. And then Nathan has this theorem in his 2015 paper that an arc alpha 1 forces another arc alpha 2 if and only if alpha 1 is a subarc of alpha 2. We haven't talked about subarcs, so let's do that now. So the idea of a subarc is that you cut off one or both ends of the arc that you've started with, and then you can take the top or bottom if you cut off one end, or you can take the middle if you cut off two ends. And then you just want to connect at the point, connect to the point at the height of your cut. And the only requirement is you stay to the correct side of each point between your new top and bottom. Words are interesting, but pictures are better. Here's an arc from 1 to 5. It goes left of 2 and 3 and right of 4. Here are 4 subarcs, 4 valid subarcs of this arc. They're not all of them, they're 4 of them. So we could cut our original arc at 4 and take the bottom, and this would be a valid arc. We could cut our original arc at 2 and take the top. This is a valid subarc. We could cut at 4 and at 2, and we would take the middle. Or we could cut at 2 and 3, and we would take the middle, which would just be the single arc from 2 to 3. Is everyone with the idea of subarcs? Cool. All right. So, so this is the idea that we've got coming from type A. We really want to generalize this now to type B and type D because they're more kind of interesting cases. So sign permutations. A sign permutation on n is a permutation of negative n through n, skipping 0, written in from pi negative n to pi n. And this midline just gives us like the trigger visually for the symmetry. And then we've got this requirement that pi negative I is negative pi I for all I. And really what that means is if we're looking at -2 in the sixth entry, we should have a +2 in the -6th entry. And that's really what we see. Hold on, computer charger needed. But then, so I also want to introduce a way that I've learned to think about this. I forget where I learned it, but another way to think about this is you've got n cards with 1 through n on your cards, and you can permute those cards, and you can also flip them over, and they've got the same number in a different color on the other side. So permute the cards, flip any number of them over, you get assigned a permutation. And if you imagine this idea of like cards on a table, flip some of them, permute them. If you know what's happening where you can see it, you can predict what's touching the table, right? And really, that comes from this symmetry idea, or we can translate through that symmetry idea. Because of the symmetry of sign permutations, they can be completely understood using what's called the window notation, which just considers pi 1 to pi n. So instead of writing 18 terms in our original example, we can just write 9 of them. So instead of writing all 18, we just start after that vertical line, which is another use of the vertical line, is to say, here's our window, here's the non-window. Another thing that's nice because of the symmetry is that if we have a descent from I to I plus 1 in the window, we'll have a matching descent from pi negative I minus 1 to pi negative I. So thinking about that, we've got this 2 negative or 6 negative 2, which is a descent. 2 is greater than negative 6, or yes. 6 is greater than negative 2. 2 is also greater than negative 6. And so we've got these matching descents in the window and the non-window, for lack of a better phrase. And the set of sign permutations on in under composition is a type BN Coxeter group. Here is the presentation. We've still got the I plus 1 being 3. We've still got just disjoint cycles commuting, and then we've got this M1, 2 being 4 because our because S1 is swapping 1 and negative 1, and things get a little bit more involved. But here's our presentation. We don't need to dwell on it a ton. Here's our weak order. 48 elements in this weak order. Going up in the weak order is done by either swapping 2 adjacent elements to create a descent in the window, or by changing the sign of the first element from positive to negative. And this is how we can build a weak order on BN. This is still the right weak order. And so as we go to think about what type B non-crossing arc diagrams should look like, we think they ought to look like a type A non-crossing arc diagram, except for the fact that there should be 2 in dots, right? Because going from negative n to n, those dots should still be in a vertical line. And then descents in the window should match up nicely with their opposites, whatever that means. And then we also know that we might have descents from pi negative 1 to 1. And as with like the squishing to the vertical line in our type A, those should still respect the rest of the sign permutation. So for the example, negative 2, 3, 1, negative 4, negative 5, thinking just in the window. Here's the non-crossing arc diagram that you might build for yourself. So if we look at the descent from 1 to negative 4, we have this arc, and it's going to match with a descent from 4 to negative 1, which is that arc. We've also got a descent from 2 to negative 2. And in order to respect the rest of the arcs, it's going to end up being this like S shape. And you might notice this non-crossing arc diagram is symmetric over 180-degree rotation. We're going to get the same arc if we flip it, or non-crossing arc diagram in total if we flip it in that way. And this is fine. This is a valid way to think of things. The delta is really analogous to the delta we looked at in type A. But it's also kind of tedious to think through examples and draw things. You're drawing 2 in dots. And so, and because it's symmetric, we can think like, okay, well, maybe there's a slightly, not better necessarily, but a different way to think about it, which is just say, okay, well, just think about the top half. So if you cut at kind of at 0, quote unquote, we know this arc from 4 negative 1 matches to the arc from 1 to negative 4. Well, then let's just connect them at that cut point. And then the arc from 2 to 0, so to speak, matches the arc from 0 to negative 2. Like we've got this symmetry. And so what we actually do is we use an orbifold point, which if you're not topologically savvy, which I'm not, this is actually an orbifold point if you are, but this idea of like cutting it in half and connecting things you know are related to each other, this is a valid way to think of it. And we have to draw less dots when we do this. So instead of drawing 2 in dots, you draw in dots and then a cross at the bottom for our orbifold point. And this is also a valid non-crossing arc diagram for type B. And yeah, it's simpler, easier to do. You don't have to worry about drawing a symmetric example every time you go to think about something. The delta is a little bit less straightforward, but still good. Okay. Here are the 48 non-crossing arc diagrams in type B in the orbifold point of view. So you'll notice some of these non-crossing arc diagrams really look like type A with the next at the bottom. Some of them look like they are type A, but if the bottom were an X. Some of them circle the orbifold point, and then some of them are combinations of different things, right? Of a type A with an X at the bottom and going around. So these are the 48. Yeah. And as it turns out, the join-irreducible elements in B3, when we think about the orbifold point of view, are still the non-crossing arc diagrams with a single arc. If we're not in the orbifold point of view, we have to have a little bit more finesse in what we're thinking about, but here are all the join-irreducible elements of B3. There are 23 of these. So congruences want to know a lot about the combinatorics of a structure, of something we're thinking about. Subarcs are forcing as a way to consider congruences. If we can think of a subarc analog in type B, we can come up with a parallel idea to the theorem that Nathan had. And so let's think about subarcs in type B. They require a little bit more finesse. So here's a long arc from 5 to 3 that rounds our point, our orbifold point. And let's think about what subarcs could look like. So we can cut the left side, which goes up to 5. We can just say, okay, we're going to start it at 2 instead. And this non-crossing arc diagram, that's still an arc, still a valid arc, looks like things we like. We could also say, instead of starting the right arc at 3, let's start it at 1 instead. This is still fine. If we try to start our left-hand side at our left side of our arc at 3 instead of at 5, we end up with this arc that starts at 3, goes around the orbifold and comes back to 3, and it goes both right and left of 1 in a way that's like, it upsets our delicate disposition. This is no good. We've kind of got the idea. If you think about the compatibility, things get upset. And then finally, we also can't just say, okay, well, I'm going to start the right-hand side of my arc at 2 and just cross it over, because that creates a cross, and non-crossing arc diagrams kind of imply that the arcs shouldn't cross themselves. And so this is also just no good. So subarcs in type B require a little bit more finesse, but we have this theorem that's in progress. We truly believe it, although Nathan doesn't believe you know something until you've checked it out. So that's all we're waiting on, is for us to do that. But so our theorem is this: a type B arc alpha 1 forces a type B arc alpha 2 if and only if it is a type B subarc of alpha, if alpha 1 is a type B subarc of alpha 2. Real parallel to Nathan's theorem. Okay, so this is the idea in type B. Let's move into type D. Even sign permutations. So in what we were thinking about earlier of cards, which you can flip and permute, even sign permutations just say you can only flip an even number of those cards. And so we've got, starting with our sign permutation idea, this pi negative n to pi n, the only difference being an even number of pi 1 to pi n are negative, so really flipping an even number of cards. Another thing is that if we know the sign of pi 2 through pi n, we know the sign of pi 1, right? Because of this symmetry idea, the only thing that could have happened is we could have flipped the sign of pi 1. So in our example, so Kyle Peterson has this notation he used in a paper called forked notation. And an example of that is here. So we have a -7, 1 negative. We have a -6, 2 negatives. 2 is even. And so 5 is going to be, this is going to be our pi 1. And -5 will be our pi 2, or sorry, pi -1. But the nice thing about forked notation is you just write 2 through n, and then you can go back and kind of figure out later if you want to think about which one should be 1 and -1. But this notation is just useful, as it turns out. And the set of even sign permutations on n under composition is a Coxeter group of type D sub n. Here is the presentation. We've still got adjacent transpositions having order 3. Our S1 changes to become two transpositions. This just preserves the order, like whether it's even or odd. So it preserves the fact that it's an even sign permutation. And And so if we wanted to think about non-crossing arc diagrams in type D, we could relate it to type B in the same way we related B to type A. And the non-crossing arc diagrams in type D ought to look like type B non-crossing arc diagrams, except that there should be no centrally symmetric arcs if we're thinking in the 2N dots, or arcs connected to the orbifold point if we're thinking in the orbifold case. This comes from what we define to be descents in type D. What have already been defined as descents in type D. That's where this no orbifold arcs comes from. And then some diagrams should also be, so the other thing is that type D non-crossing arc diagrams, some of them are equivalence classes of 2 type B non-crossing arc diagrams. And then we also need to be careful about the idea of compatibility. It needs to expand a little bit to allow for kind of sharing descents. Pictures are worth 1,000 words. Here are the 24 non-crossing arc diagrams in type D, where each box is one non-crossing arc diagram. So we've got something that looks like a type B non-crossing arc diagram here, right? Circles the orbifold point, single arc. But we also have these 2 arcs being identified with one another, two type B arc diagrams being identified. And then we also have this interesting thing that can happen on our bottom left, and then on a couple other diagrams as well, where we have a shared top endpoint in both of our non-crossing arc diagrams in type D. So things have gotten a little bit squirrelier still. And if we wanted to think about the idea of forcing via subarcs, thinking about join-irreducible elements, we're still going to have single arcs, but like this box is a join-irreducible element in type D. It's a single arc, except that it's 2 representatives, which are both a single arc. And so when we go to think about subarcs, things require even more finesse, because we could think about what's the relationship between each of those and each of those representatives. So we've now got like more representatives to consider, and those representatives were type B to begin with. And so things are a little bit more dynamic in type D. But we think the principle should still hold. We don't have like a theorem that we just need to check out. We're still understanding what is going on in type D. Okay, so we're now into bonus material.
I have a question.
Yeah.
For now, what would a centrally symmetric arc diagram look like? That wasn't clear to me.
So
in the
the
previous
centrally
slide.
symmetric arc.
Yes.
Um,
Yeah.
So let me go back to, going all the
Is
way
that
back.
the 180-degree rotation?
Yeah, it's
the
a
same?
single arc. Let's see, hold on, I just lost my place. Okay, hold on. I apologize for the vertigo.
No problem.
Okay. Okay. So yeah, I guess I didn't use the terminology here. The arc from two to negative
Mhm.
2, this is what we're calling a centrally symmetric arc, as
Gotcha.
opposed to a pair of arcs. So the centrally symmetric arc idea is really when we're thinking in the 2N, and it translates to the orbifold, like the arc that
Gotcha.
touches the orbifold.
Thanks. That
Yeah.
clarifies it.
Great. Any other questions before I get into bonus material? Okay, cool. So we're going to just switch gears a bit. Oh, I see something in the chat. Yes, the arc gets sent to itself in 180-degree rotation. Thank you, Mark. And I now have the chat up, so I'll see it. Okay, switching gears. So if we have 2 lattices, L and M, that are non-empty, where M is a subset of L, M is a sublattice if for any pair of elements in M, the meet and the join from L are still in M. This also translates to M being a sublattice of L if they have the same meet and join operations. So kind of a vague idea there, but well, not vague, meets and joins. So we're going to build to what is the shard intersection order first. So we had at the very beginning that the Coxeter group presentation included an SI squared to the identity for all I. So we can really think of these SIs as defining a reflection. Each generator defines a reflection in Rn. And we're going to think of those reflections as being across hyperplanes. And then additional relations tell us the angles between the pairs of hyperplanes. And then they'll also generate additional hyperplanes from just our generating, our two generating or however many generating hyperplanes. So we've got the A2 and the B2 hyperplane arrangements here, where the generating hyperplanes are highlighted in gray. They're great. Okay. So the hyperplane arrangement, which we use this MathCal A, cuts out regions which happen to be closed, full dimensional, and actually simplicial cones in Rn. And these regions correspond to elements of the Coxeter group. And in fact, for any Coxeter group W with generators S, the fan defined by A is the normal fan of the type W permutahedron. So looking at the dimension 2 case, we've got S1 and S2 correspond, or the region between those two corresponding to the identity. And then we end up with the hexagon. And then in B2, we get our octagon from those. And I've just rotated the figures from the last slide so that our identity element is at the bottom because I just can't stand anything else. But yeah, we've got this nice correlation between the two and really like that bijection from regions to elements in our post set. Did it not change? Sometimes it just decides to stop mirroring. Now we're gonna try it again. Okay. Okay, and we're back. So given an, let's see, we are in fact still building. Okay, so given an arrangement A, we're gonna let B denote the region corresponding to the identity element, and then we're gonna call that the base region because B for base, yeah. Okay, so then given two hyperplanes H1 and H2, we have this idea of a rank 2 subarrangement, A prime. That should be a Cal A, but it's made up of all of the hyperplanes crossing through the intersection of H1 and H2. And then in order to have things look nice, we're going to preserve the angles from Rn down into R2. And so in a rank 2 subarrangement, exactly one of these regions will contain our original base region. And we'll call this region B prime because prime, and then we'll call the two hyperplanes that define that B prime basic in that hyperplane arrangement. So far, generally okay. All right. Finally, we've gotten to shards almost. So a hyperplane H1 cuts another hyperplane H2 if there exists a rank 2 subarrangement A prime in which H1 is basic, so touching that new base region, and H2 is not. So we've got an example down here at the bottom where we've got H1 and H prime being the basic hyperplanes in this rank 2 subarrangement, and then H2, H3, and H4 are not basic. And so H1 is said to cut H2. And cutting brings to mind the idea of disconnecting. And in fact, the segments of H2 can be thought of as being disconnected by H1 when H1 is basic and H2 isn't, and by that cutting relation. And then the shards of H are the closures of the disconnected segments defined by all of the hyperplanes that cut H. And so these aren't, so we've got this hyperplane H2, which is cut by H1 and H prime. And this doesn't actually split it in the way that we have, but removing it from the origin lets us see this is broken into two shards in this hyperplane arrangement. We could consider other rank 2 subarrangements where maybe H2 is cut again by another basic hyperplane. Okay, so this is the idea of shards. Yeah, Mark.
So because we're taking the closures of these disconnected segments, they're still all going to contain the origin, right?
Yeah.
Okay.
Yes. Yeah. And because we're taking the closure, we can think about intersections in a way that's useful. So intersections of shards are partially ordered, we can partially order them under reverse inclusion. So just to be clear notationally, so we can think of sigma 1 is less than sigma 2. Sigma is the notation used for shards, and this is true if and only if, well, okay. We're going to take intersections. But so one intersection is less than another if and only if that intersection, contains the other. I'm going to call them A. Oop. And the intersection of some sets of shards. Okay, so we're partially ordering under reverse inclusion, and the intersection makes sense because even if we only meet at a hyperplane or at a plane, what am I thinking? In a linear idea, that we're still good. Like they can meet at borders. This is fine. Okay, and then each region defined by A. Which again, remember, is in bijection with elements in the poset, in the lattice given by our weak order. Ooh, that phrasing I didn't love. That's okay. So each region defined by A has a unique set of lower shards which touch it. This is just like, it maybe is not obvious, but is true. And then each of these regions corresponds to a joint, or each of these shards corresponds to a unique joint-irreducible element in the weak order. And we can take intersections of these lower shards. So we think of a region, and then we think of what are all the shards that are on the bottom of that region when we think of the base being at the bottom. And then that's going to get us to an intersection of shards, which we then order using reverse inclusion. This is all very like 30,000 foot view of what we're really doing, but it gives us the following orders. So here's the shard intersection order for type A3. It's like much flatter than the weak order was. We've got 1, 11, 11, 1 as the sizes of each of these ranks. And as you can see, very crisscrossy, very unpleasant to look at, very unpleasant to think about. B3 is worse. 1, 23, 23, and 1 are the sizes of each of these ranks. Okay, so shard intersection order is interesting to think about. And the question that I was given by Nathan a year ago, I guess, is the shard intersection order of type A a sublattice of the intersection order of type B for AN and BN? And because non-crossing arc diagrams are this cute, strong visual tool that actually know combinatorics about permutations and sign permutations, I started looking at those, and they suggest this answer, which is yes. The way that we get to this yes is something that was known was Rodica-Simeon had a homomorphism from type BN to type AN, which is good in the context of weak order. So it's a homogeneous degree to, it defines a homogeneous degree to congruence, and it's fantastic. And there's an astoundingly nice injective homomorphism, as it turns out, going from that uses type A diagrams going to type B diagrams in the orbifold view, which matches exactly Simeon's algorithm, or homomorphism, not algorithm. So just a brief example, if we've got the non-crossing arc diagram in type A, this is, no, it's not, it's 3, 4, 2, 1. If you just imagine taking, so this is in type A3. If you just turn the bottom dot into an X, that gives us -1, -3, -2 should be after -2. Yes. It just like, wow, it works. Yes. And so this homomorphism matches with Simeon's homomorphism. And then you can think about, or I've been thinking about what meets look like in the shard intersection order using non-crossing arc diagrams. And I've gotten to the idea that, in fact, a type A sub n weak or shard intersection order is a sublattice of the shard intersection order for type BN. And that is all I've got. Here are some references. Thank you again so much for coming, and yeah, any questions?
All right, thank you, Ashley. Let's all thank the speaker with reactions. That was very nice. Thank you so much. I have a question to start us off. The very nice injection, was that just replacing the bottom point with the orbifold point? That
Yeah.
was all it was?
Yeah.
That's really cute.
It's very cute. It's annoyingly cute. I did spend like we all spent a lot of time thinking in the 2n dots. And so like these centrally symmetric curves or the pairs or whatever. And I spent a lot of time thinking about like these homomorphisms and what they looked like getting from the type B to the type A. And then Nathan introduced the orbifold idea. And I was like, oh, I got to get a handle on this. Like I'm going to draw and it was like, oh, 24 of them don't go around the orbifold point. I wonder what those 24 are. And it's like, oh, those are the exact ones that are, and I was like, oh, I crumbled, but it's fantastic. I mean, it's really great. Would have been nice to know earlier, but I know so much about those 2n. Yeah.
Awesome.
Yeah, thank you.
Other questions?
I have a question. This is what is the origin of the concept, the non-crossing arc diagram? Like, was that, who first came? Where did some motivations come from? And remind me who first came up with it.
Yeah, so Nathan first came up with it. He brought it up in his first paper on it was in 2015, and it says non-crossing arc diagrams and canonical join representations. And so non-crossing arc diagrams actually give a really nice visual idea to the canonical join representation for a permutation. And so he came up with it in 2015. And so it's fairly new, and yeah. Nathan Reading came up with it. And so the idea, it knows a lot when we're thinking about like interesting combinatorics. So actually the left non-crossing arc diagrams on type for, they're the Catalan number, or yeah, they are counted by the Catalan numbers, because you can imagine just turning a left diagram into a circle, and then you've got non-crossing partitions on in. But yeah, it's just this like really cute tool. I mean, cute not to be diminutive, but like it's so cute, and it's also incredibly strong, and so it's a really great tool.
I have a question.
Yeah.
I don't know, the really great talk, by the way. I really enjoyed it. Yeah. Okay, I don't know if this makes sense, but a lot of the things that you use to define your diagrams are like things that exist for all Coxeter groups, like descent and things like that. Is there any way to take what you now have for like type A, B, and D and like come up with a general Coxeter formulation that like somehow enumerates like just the elements of the Coxeter group?
So we haven't done that yet, but we have thought about, we haven't done that yet, but we've thought about thinking like, okay, well, could we extend it to H3? And we haven't, but it suggests that they're like, it feels like there should be a way, right? It just becomes an issue of like, okay, well, how do we get a computer to throw out what we want? And also, to my understanding, which is very remedial still, I don't know that H3 has like cute things given by it in the way that like B and D, this idea of like, oh, it's even sign permutations, it's sign permutations. It's like H3 is just what it is, it's 120 elements with all these fives. And so it's like, we haven't done it yet, but it is an interesting idea to keep working towards.
Yeah, I don't think you could use like permutation type things. It would have to sort of, there would have to be like a step before that like generalizes the things you have to Coxeter language.
Yeah.
Cool. Thank you.
Thank you.
We have a question in the chat Oh,
Okay.
so the question in the chat was, one, this is a really interesting subject, and can you suggest literature on the topic? I guess those two papers at the end are a start. Is there anything else you would suggest?
You know what, actually, let me pull up, there is a third paper that we didn't know about when we started our work by Pedral, Pilot, and Ritter that I can share the archive link to. One of the interesting things is that like non-crossing arc diagrams are like, they're fairly new. And so I'm really thinking about using non-crossing arc diagrams in the context of shard intersection order. And it turns out there's some traction there. But yeah, the paper by Nathan, that non-crossing arc diagrams and canonical join representations is a great place to start like archive chasing.
Okay, I also had a question.
Okay.
Well, I have two questions. So we'll start with my first one, which is, so if you go back to like slide 25, I think, and
Okay.
so you were looking at the BN non-crossing arc diagrams,
Mhm.
and you noticed that, oh, these are rotationally symmetric. And so
Mhm.
eventually you came up with the orbifold point, like we can cut them in half vertically. But you could also cut them in half horizontally and keep all of the information.
Yeah.
And so I was wondering if y'all had looked into that, if that gives you other interesting combinatorics. So instead you just have.
Huh. We have not, but that is an interesting point. Hold on, I noticed it wasn't updating. I had moved to the page that you thought of. And then it didn't reflect here. Okay.
Yeah, I don't know if 25 is exactly the page I wanted, but this was the type B stuff.
Yeah.
And so I just was like, yeah, if I cut this horizontally, like I know what's happening on the left half because.
Mhm. Right. Yeah, it's definitely interesting. One like, yeah, okay. Yeah. One interesting thing is what happens to the line that was here. Like we have to still remember it, but but we're up to combinatorial equivalence, so we could just draw it a little bit differently. And instead of having a vertical line be really a vertical line, it's either right or left or both. I don't know. It's interesting.
Okay, yeah. So that was the first thought. Is I was just like, oh, I could, because before you cut it vertically, I was like, yes, I can cut this horizontally, and then I went, oh, that also works. The other question I had, though, I'm checking to see if I'm interrupting anyone else, is that, so you notice some subarcs of an arc are also subarcs of other subarcs. So you have a partial order on your subarcs.
Yeah.
Does that correspond to something in your Bruja order?
So there's something called the forcing order.
Okay.
Turns out this idea of some things are subarcs of other things as well, gives us what's called a forcing order. And it turns out the forcing order is really useful. So yeah, we've got this little arc forces this, the 2 to 4 arc, the 2 to 4 arc forces a 1 to 4, and then this forces, and so it gives us a graded in type A, and in type B it gives us 2 graded posets. They're not lattices, but we've got graded posets in type A and type B. In type D, we lose the grading in thinking about the forcing order.
Okay.
But yeah, the idea of subarcs being a sort of transitive gives us good stuff.
Okay.
Yeah.
I have another question also. So I know there's like rules with these diagrams, so maybe the answer to this is no, but is there like even in type A, an action of like the symmetric group on these diagrams? And if so, have you looked at like the orbit structure at all?
The action of these diagrams. So will you repeat your question one more time?
Is there a way that the symmetric group like could act on these diagrams at all? Because they're so, I mean, they're just so related to permutations and they're kind of labeled. It feels like there should be some way to
Yeah, so the one example that so I haven't thought about this generally. It's possible Nathan has. I haven't. But there is one thing that you can do where if you conjugate by the longest element, why would I do? I'm not going to write it like that. So if you conjugate by the longest element sigma, you swap the in the permutation, you like flip the order backwards, and then you also flip the orders of the elements. There's this, and what that does to the non-crossing arc diagram is it rotates it by 180 degrees. Which also has us, it gives us context for type B, the type B idea where we use 2 in dots, because type B sub n is a subgroup of type A sub 2 n minus 1. So the 10 dots is a subgroup of, if we just had S10, right, which is A 9. And so it makes sense that this and the type or the even sign permutations are invariant under that 180 degree flip. Yeah. So that's the one thing that I have thought about, but only because it's already been thought about before. I don't have other examples, but it'd be interesting to think about, like, okay, yeah, what happens?
Cool, thanks.
Yeah, thank you.
All right, let's thank the speaker one more time. Thanks, Ashley.
Thank
Now we can
you.
stop the recording and ask